All right, let's do a little power rule proof. Okay, so this video is going to take you through a proof using the definition of the derivative of our power rule. Remember, our power rule is if we have some function a x to the n, how do we take the derivative? Well, we bring down the power and decrease the power by 1. So like if we had a function 3x to the fourth, we bring the 4 down and make it 12 and decrease the power. And so the derivative of 3x to the fourth is 12x cubed. And I'm going to use the definition of the derivative to kind of prove this in the abstract. Okay, so what we're really working on here then is looking then at using this as our function and going ahead and using this definition. So we're going to look at the limit as h goes to 0 of f of x plus h. Well, that's just a times x plus h to the n minus a x to the n all over h. And we just need to simplify that. And again, what we're looking at here is we got to expand this. So I'm going to come down here and kind of look at some expansions. So what if I had x plus h squared, right? What if n was a 2? Well, this would be a times x squared plus 2xh plus h squared, okay? What if it was a cubed? I'm trying to find this pattern here. X cubed plus 3x squared h plus 3x h squared plus h cubed. And again, I'm multiplying all this out and I understand the pattern. You might have to take out a scrap piece of paper and kind of figure out how in the world I'm figuring these out, but this is the pattern you would get. This would be a, and this would be x to the fourth plus 4x cubed h plus 6x squared h squared plus 4x h cubed plus h to the fourth. Okay? And what we really want to decide is, we could just keep going, is how in the world are we going to expand a times x plus h to the n? Okay, so it's going to turn out that if you expand that, again, we're looking at the limit as h goes to 0. What you would get here is you would get a times x to the n plus n x to the n minus 1 times h plus n times n minus 1 over 2 x to the n minus 2 h squared plus dot 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 dot. You keep getting all of these extra terms, and the last one would be h to the n. Okay, what this red here is what this is, a x plus h to the n, where we don't know what n is just some variable. Okay, and then we have to still subtract ax to the n, and we're looking at that limit as h goes to 0. Okay, so hopefully you can see that if I take this and I multiply this a, all of these terms just get an a, and I'm going to have an a x to the n, and that's going to subtract from that a x to the n, and then all of these are left. So I have a n x to the n minus 1h plus a n minus 1 over 2 x to the n minus 2 h squared plus dot 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 a h to the n all over h. We're going to look at the limit of that as h goes to 0. Okay, all of these terms that are left have an h. I can factor out an h and I can cancel. Okay, so I take out an h, again, rewrite the limit. I can take out an h, and I'll be left with a n x to the n minus 1 plus a n minus 1 over 2 times x to the n minus 2, and that would just have one h left. All of these other guys would have one less h. So this would be h n minus 1 all over h. That h now cancels, and now I can look at the limit as h goes to 0, and look, this doesn't have an h anymore, and all of these terms have an h. And so when you look at the limit as h goes to 0, all of these guys will go to 0. And the only thing left is a times n x to the n minus 1. And then we've derived the power rule. Again, we use the definition of the derivative. We use some expansions, right? We had to expand x plus h to the n, and we've developed this pattern for what the coefficients are. The first coefficient was 1, and then n, and then this, and it kept going, and the last coefficient was just an h to the n. See how it's symmetrical? This is x to the n with no h's, and we keep getting one less x and one more h. And then we keep going down, and the very last term doesn't have an x and has all the h's. Okay? And what we could do is that this lead term cancels. We can factor out an h from all of these terms that are left, which is what I did here. And we can cancel the h in the denominator. All of these terms still had an h in them, so when I looked at the limit as h goes to 0, I keep plugging in 0 for all of these, and that all of those then go away, and the only term left that survives the limit is this. And so the limit of this function is a times n times x to the n minus 1, which is exactly what the power rule says. If you want to look a little more about how I got these coefficients, it's really the binomial theorem, which ends up figuring out what these coefficients are. And it's one of those things that the coefficients end up being n choose k. That's the notation you'd look at if you looked this up. And n choose k is how we talk about the number of ways to choose k items from a list of n items. And it's n factorial over k factorial times n minus k factorial. And again, you can go through and figure out that this first coefficient is n choose 0, n choose 1, n choose 2, n choose 3, n choose n. And it just gives you this whole list of what it is. If you'd like to see kind of a short little demo here, and then I'll turn you loose. If you had 5 choose 3, that's 5 factorial over 3 factorial, and then 5 minus 3 factorial is 2 factorial. Okay, that's 120 divided by 6 divided by 2, right? That's 120 divided by 12, which is 10. Okay, that's saying that there are 10 different ways to choose 3 items from a list of 5. And I'll kind of list those out for you. Make sure I don't forget any. But if we take the 5 letters A, B, C, D, and E, okay, so those are our items, A, B, C, D, and E, I can choose 10 different ways of picking just 3 of them, okay? A, B, C, A, B, D, A, B, E, A, C, D, A, C, E, A, D. So those are all the ways to pick with A. So like, okay, don't include A's now. Okay, so there's B, C, D, B, C, E, B, D, E. Those are all the ways that have B's that don't already have A's, and then there's really just one left, C, D, E. Okay, so those 10 different ways to take 5 items and pick 3. And again, you can also look at not the Pythagorean theorem, Pascal's triangle is another real cool way to establish those coefficients in the same manner. And so if you look at Pascal's triangle and you keep going down, all of these coefficients are exactly the coefficients, and you can compare. Look at this line right here and look at those coefficients. 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. Look at those. 1, 3, 3, 1. 1, 3, 3, 1. These coefficients, 1, 2, 1. 1, 2, 1. And the same thing, this number here is represented by this kind of notation in upper level math. So if you like that sort of thing, and you can kind of look up more stuff on, this ends up in a decent amount of probability and statistic lessons. And this Pascal's triangle has a lot of really cool things, but certainly multiplying something out like this triangle is pretty helpful. Okay, so hopefully you enjoyed the proof of using the power rule. This proof, it really only proved that if an n is a positive integer, but you can look up more complex proofs that proves that this actually does work if n is a half, or n is -3, or really n is any real number. Okay?